Thank you, Mr. Chairman. The variational principle has, first of all, a mnemonic value that allows to deducing the physical law in a systematic and consistent way. Today, there are overall a powerful tool to construct approximations, especially for numerical simulations. The convex analysis and the differential geometry are two disciplines which usually aren't working together. Is it possible to combine them? It is useful. Yes, it is, as we'll see, and how. Already 200 years since the discovery by Navier of the famous equations which is named after him and Stokes. It is what I'd like to celebrate with you by presenting this work. Have a look to the literature. Nowadays, there are several unified mathematical frameworks for dissipative systems. The three former ones being the most popular. However, in this work, I'll use the one of Hamilton inclusions proposed by Marius Boliga and developed later on with me. Concerning the variational formulations of Navier Stokes equations, there are a lot of work, but starting with pioneering works by M. Holtz and Rayleigh. One can also mention the formulation based on Onsager theory, the one of Glanzdorf and Prigogine, who received the Nobel Prize, and likewise of Lebon. He was my professor. More recently, a modification of Hamilton's principle was proposed by Fukagawa and Fujitani, and in the same spirit, but different presentations by Gay Balmas and Yoshimura. However, the nearest formulations to mine in functional analysis is the one of anti-self-dual Lagrangians of Goussot that I'll comment later on to emphasize the resemblances and differences. First of all, we have to identify the symplectic formalism able to modelize the motion of reversible continua in the spatial or Eulerian description. That requires the following modeling of the matter and its motions by a line fiber bundle with a projection pi 0 from the space-time of dimension 4 onto a matter manifold of dimension 3. So the fibers are lines, physically the trajectories of particles. And in local chart, an even bold X is represented by a column collecting the time and the position, while a material particle, bold X0, is represented by a column X0 collecting the Lagrange coordinate. Finally, the projection is represented locally by functions by x0 as a function kappa of the event Tx. It is well adapted to the Eulerian descriptions in contrast to usual formulation where x is a function of t and x0. It is our first K point. Now, these Eulerian descriptions also require a special version of the calculus of variation that I call by jet theory. I refer to the presentation by Castrillon yesterday. First of all, we have to take care to don't fall into a trap. As L and H are density, pi dot v is the same. But the velocity v is one contravariant. So then the momentum pi must be one covariant and antisymmetry 3 contravariant. It is another key point. We consider the Hamiltonian of the system at time t. It is a functionals depending on the field x0 and pi. We claim that the motion of the continuum is described by the canonical equations where at the left zeta is a compound of the velocity and the partial time derivative of pi, and right xh is the Hamiltonian vector field for the following canonical symplectic form. H is a functional, so xh is a variational derivative, which is calculated in 3 steps by jet theory. First, we perform a new parameterizations of the variable x, which is now an artificial field psi. Next, we calculate xh by taking the variation with respect to the field x, x0, and pi, taking into account the transformation law of the 4th rank tensor pi. Finally, to eliminate the artificial field, we consider the limit y converges to x. I skip the technical details and I present the final result, the corresponding canonical formulations, where the former equation is classical. The second one contains in red unusual extra term stemming from the jet theory. And for classical Hamiltonian corresponding to mechanical problems, we recover from the former equations the definition of the linear momentum. And from the second one, its equation of conservation. In fact, it is Noether identity obtained by jet theory, where phi and a are the scalar and vector potential of the Galilean gravitation. For the particular case of barotropic 3, we recover Euler's equations, but in a covariant form, consistent with Galileo's principle of relativity, where g is the gravity and omega is Coriolis vector, useful for applications to environmental fluids, atmosphere, oceans, and Earth interior. Now, I write to my goal to construct a symplectic minimum principle for dissipative media. It is inspired for pioneering works by, at the left, I'm Bretzis, middle, Ivar Ekeland, and right, the late Bernard Nerol. For dissipative continua, we decompose the velocity data in a reversible and irreversible part, zeta I. The idea being that if the system doesn't dissipate, we recover the zeta I is 0, and we recover the canonical equation of the reversible medium. Now we need extra rations that I call the dissipative constitutive law, zeta I, that claims that zeta I is the Hamiltonian vector field of a dissipation potential phi. This derivative being defined rigorously by these conditions. In fact, it is a variational derivative. Now, in physical applications, we can suppose that this potential is convex. Now, we invent a new derivative, the symplectic Fenchel conjugate phi star omega. Simple sleight of hand. In the definition of the classical Fenchel conjugate, we replace the dual pairing by the symplectic form. So because of the supremum, it satisfies a symplectic Fenchel inequality, this one. And in the limit case where the equality is reached, it can be proved easily that the dissipative constitutive law is equivalent to these relations called the extramelity conditions, K point, which is a crucial K point in what follows. Now, starting from the original idea of the three previous authors, with Marius Boliga, I propose a symplectic version of their principles. An evolution path in the space of couples of motion kappa and velocity zeta is said admissible if it satisfies the initial and boundary conditions. That, of course, must lead to well-posed problems, but of which we don't need to give the explicit expression. Now, I can state the symplectic Bredsis-Ekelund error as then, in short, that claims that the natural evolution path minimizes this functional among all the admissible evolution paths. Let me give you a few explanatory words. The functional is constructed from the dissipation potential, the Hamiltonian for the reversible part of the behavior, and the symplectic form for the dynamics. According to the symplectic Fenchel inequality, the minimum is 0. And it is reached by the natural evolution paths because of the extremality condition. Now, zeta I has two components, Vi, Pi, of which the expressions is deduced from the canonical equations. Now, this is the last K point. We need a strong hypothesis that the partial time derivative is ignorable in the dissipation potentials. In other words, it depends only on the velocity. Then it can be proved that the symplectic Fenchel conjugate has a finite value equal to the classical Fenchel conjugate, phi star, with the argument minus pi I, if and only if Vi equals 0. So because of these conditions, the last term in the functionals containing the symplectic forms is simplified, this disappears. Finally, the S-band functionals is reduced to this one. Well, in the integrand, the two former terms is, in fact, Goussup's anti-self-dual Lagrangians, where the puzzling sign minus reveals, in fact, its symplectic origins. Some of you could say me, but where are Navier Stokes equations in all of this? It is what we are going to see now. This is the S-band principle applied to compressible Navier Stokes equations. It is the functional is obtained simply replacing in the previous expressions pi I by replacing pi I by its expressions. Now, it's interesting to remark that for the limit case of inviscid flows, that is reversible behavior, of course, the potential phi vanishes. And it can be proved that Fenchel's conjugate phi star has a finite value equal also to 0, 1 pi equals 0. These last conditions, the meaning is simply Euler equations. Then, the S-band principle claims that the remaining term, the time integral of this, is in fact the total heat loss is 0. That is the expressions of Bernoulli's principle. It is very nice. Finally, it is worth to note that in this limit case, the S-band principle doesn't degenerate into Hamilton's principle. It is of a different nature. Finally, we need a second hypothesis, which is classical. 5 depends on the field V through the strain rate that denote D. And it is quadratic to have a linear behavior. With respect to V, well, W is a dissipation density is given by this. So then the viscous part of the stress tensor sigma I derivating W with respect to D is traced according to Stokes hypothesis. Now, we can prove that the principle of minimum restitutes Navier Stokes equations. Indeed, if the minimum equal to 0 is reached, we have almost every other in the time interval these relations. In fact, the extremality conditions that we have seen to be equivalent to the dissipative constitutive law reduced to this form because of the first hypothesis, and where nabla-V is a variational derivative given by minus the divergence of sigma I. Combining with Stokes hypothesis, we recover Navier Stokes equation. This is now we consider the limit case of incompressible Navier Stokes equations. In this case, the pressure P becomes a free variable independent of the motion. To obtain the corresponding S-band principle, the internal energy is cancelled in the functional and the Hamiltonian. The incompressibility conditions is introduced as a constraint in the minimization. So the pressure disappeared of the functional with the internal energy and reappears, of course, as a Lagrange multiplier of this constraint for the minimum condition. It is time to conclude. I would like to emphasize the advantages of the new formulations. First, the present variational approach covers a large class of problems, including Navier Stokes equations, but also set-valued dissipative laws such as Bingham fluids, fracture mechanics, and plasticity. Second, the expression of the functional is, in contrast to Gauss-Hoops formulation, is independent of the boundary condition that appears only as constraints of the minimizations. The functional is not convex, but there is at least partial convexity that is favorable for the convergence of the minimum algorithm. Finally, it paves the way to provide variational approximations of the solutions. In particular, I tackle analytical examples, but I believe that the most promising perspective concerns numerical applications, developing, for instance, symplectic integrators based on these formulations, and constructing variational schemes based on the S-band principle. Finally, functional analysis aspects in Gauss-Hoops theory could be revisited. For the technical details, if you are interested, I refer you to my archive publications. Thank you for your attention, and thank you to Claude Louis Navier and George Gabriel Stokes, these two benefactors of humanity who would deserve also, as Hamilton, to be celebrated for their discovery by a stamp.
So when I compare this approach to the introduction of fractional terms in variational principles, right? So there, if I introduce fractional derivatives, I lose in a sense locality, right? Because they are not. Yes. So, but do you also buy the dissipative terms by losing locality of the definition of the Lagrangian density? It looks like this is exactly the integral sign that is in your Lagrangian.
You can see the particular slide? I don't know.
Yes, well, I was thinking whether there's a similar thing happening here as we know from the introduction of fractional derivatives, right? So you can also have a variational principle, and in the Lagrangian there are fractional derivatives. This is also how you can model dissipative terms, but you lose something. You lose the locality of the Lagrangian. So the Lagrangian, to evaluate the Lagrangian density, you will couple, in a sense, after discretization, all points. And I was wondering whether you see that effect as well. But maybe we should chat about this.
I don't use Lagrangian terminology because, in fact, the integrant here in the functional is not the Lagrangian of the Hamilton's least action principle. It is a very special variational principles because, in fact, the minimum conditions is not classical Euler-Lagrange equations. It is the extremality conditions. And of course, it is equivalent to equation which is similar to Euler-Lagrange equations.
The setting also for big fluids for plasticity.
Yes.
In this case, you just implement a different dissipation potential.
Yes, there was first a PhD in solid mechanics about plasticity problems, and we verified that this principle it works. It's interesting for applications, and in the future we are working now on the fracture mechanics, but also it's possible to find applications in fluid mechanics. All the behavior where there is a non-smooth constitutive law.
Professor Stokes, one more. Thank you very much.